So hi, everyone. Thanks for returning and thanks for the questions yesterday. Please today feel even more free to ask. So I'm going to remind the construction we had yesterday. So we have this object. This is the notation we have so far. So it's a Cayley square complex with three things. G is a group. A and B are subsets of the group, closed under inverses, and they don't contain the identity element. And then this gives you this graph with squares where you have a vertex for every group element, and this vertex has neighbors for every left multiplication by an A element, and for every right multiplication by a B element. And the nice thing is that this will always close a square for you, and you have here A, G, B. Okay, so that's the combinatorial structure that we're looking at. And we define the code. We first take some code CA, which is a subset of functions from A to 0, 1. Of course, the alphabet of the code doesn't have to be 0, 1, but let's take it to be Boolean. And you also have another code set B, and I'll probably assume that A and B have the same size. They don't have to be the same size, just easier to think about. And if they have the same size, you can take the same code in both instances. And then we define the code to be, okay, maybe I should just say, so we, in these graphs with squares, x0 will be the vertices. I don't think I'll really use this notation. What I do use, so x1 will be the edges, and x2 is going to be the squares. Two-dimensional faces. So my code is going to be all the functions on x2 to the alphabet. Again, can be another alphabet. Such that two things hold for every A, G, and B. We're going to require that the function, oh, I forgot to select this notation to remind the notation. This square, we called it AGB with square brackets. You have for every triple of choice from A, G, and B, you're going to have rooted square that's this thing plus the choice of a vertex, and the four different choices together are going to be the equivalence class that we denote by square bracket AGB. So AG dot means all the squares where you fix A, you fix G, and you let B run freely. This needs to be in CB, and also when you let A run freely and you fix G and B, we want this to be in CA. So that's the definition of the code. Okay, so these were the two objects we talked about yesterday. Nice thing to think about is that these are like the base code. You fix it, it's like fixed on all the squares that touch an edge. So you can think of it as the link of an edge. So since it's the link of an edge, you can think of it as C1. It's the link of an element here in the 1. And then if you think of the link of a vertex, and you ask yourself, what does the code look there? And let's call that C0. We talked about it yesterday that, so link of an edge, I'll just remind this. It looks like this. You have your edge, and then you have a bunch of squares like this one, and this one. So it's like a book with pages, and each one of these squares, these are the squares in the link. And then the link of a vertex.
This is link in one direction. You have links in two directions, right? This is like, if it was an A edge, then it's a book on the B's, and if it's a B edge.
Right, thanks. So I guess I can also draw this book. Right, so for example, if this is G and this is G times B, this is G and this is A times G, then these are indexed, these squares are indexed by the elements of B, and these squares are indexed by the elements of A. Right. So this is a link of an edge. If it's an A edge, it's this way, B edge this way. Link of a vertex. So if I have a vertex G, and I ask myself, what are all the squares touching G? Then we had this picture where I had G, and then I drew the A neighbors of G. So it's like this.
Make it 2 by 2 so it's easier to draw than 3 by 3.
I think. Okay, so suppose I have A1G and A2G. And then I also have, maybe I can use.
Yes, our colors, but not all visible.
What are the Hagoromo? Okay, so this would be G times B1, and this would be G times B2. And then if I think of this A edge, what is the book on this edge? So there's A1G times B1, that's this guy, and A1G times B2. So you see that this completes to a square and this completes to a square. And then if I look at the A2 guy, it's the same thing. I should draw this, so I'll have, now I lost it. Okay, I have this, and I have this. I guess, I don't think I succeeded so well. Okay.
The 4 antipodal points a different color, and we'll see. If you
Yeah, I
help
think
out.
so. Okay, now you can help me. So I have this guy, this guy, this guy, and
The left and
Top
up.
left.
No, small amount. Okay.
This guy?
Yeah.
Yeah, right. So they're supposed to look like a grid, a 2 by 2 grid, an A by B grid. Okay, so this is how a link of a vertex should look like, an A by B grid. I guess here it's just 2 by 2 like this, where this is the A2, this is A1, this is B1, and this is B2. And these are like the 4 squares. So
That's not like a proper link, right? Like link usually
No,
should
it's
be,
a slang.
yeah,
you're right. In a simplicial complex, the link
Like, should be
you can only
edges.
have the vertices that touch your vertex.
yeah.
Right. So okay. So I don't know.
No,
But let's use this one anyway.
linguistically, it's the link.
Right. It's the neighborhood, you know.
Yeah.
Okay, so all right, so we have this structure. So I wanted to go back to the code and say, for the link of an edge, we defined our code to be something, meaning that if you fix some edge and you look at the book on this edge, and of course we said that the squares are already arranged in a bijection. There's a bijection between the set B and the set of squares. So there's a natural way to ask whether the set of bits that you see here is an element of CB. So we require that this happens. And then we can ask ourselves, what does the code look on the link of a vertex? So now we have like a by B, a little matrix, and we ask ourselves, what does it look like? And we talked about it, that it means that I don't know if this is a row or a column right now, every row is in CA and every column is in CB. And you can see, and Alex says it's ridiculous to look at the picture, you should look at the algebra and you see it immediately that if
It's not ridiculous.
Everybody should look at what they like, and so many people like.
Sorry, I
it.
shouldn't have implicated Alex. So you can define C1 if you want to be a code it's like CA is a subset of 0, 1 to the A. I can define C1, not C1, C0, to be a subset of A cross B. It's a sum of the matrices A times B, and which ones? It's exactly those where the A rows belong to CA and the B rows belong to CB, and that's the tensor. So it just equals to CA tensor CB. Right, and what we see is that in this construction, we really have 3 levels of codes. The top link code is the one we start with. It's our base code. It's this CA and CB. Then it immediately implies that on a link, we see some interesting code, which is this tensor CA times CB. And then if we go to the link of one face down, sometimes people think the empty set, it's the entire global code, and that's our code. So if you want, you can think of this as C minus 1. I'm not serious, just to say that you have C1 and then C0 and then C minus 1. Okay, so, right. Okay, so that's the structure. Code, and let's talk about the property of the code. So, I want to talk about the rate. Maybe we talked about it, but just quickly. And then the distance. And then the local testability.
You want to tell us something about CA and CB first, or?
Right. What I wanted to do is to start seeing something about the rate, and then we'll see that it's going to be non-positive unless we assume something about CA/CB. So, this is defined in general.
Okay.
And what I can prove is that if the CA and CB have high enough rate, then this thing is going to have rate. But it's possible that our argument is not strong enough, and actually even for a broader class of CAs and CBs, there could be a rate, except that we don't know how to argue that. Because our argument is just about counting constraints. And if you think of other codes that we know they're locally testable, like the Irit Dinur codes, these polynomials, if you start counting constraints, you'll see that there exists no code word in the Irit Dinur code. So we have different reasons, how do you prove that the Irit Dinur code is not empty? You show these low degree functions and you show that they satisfy all the constraints. So this is something that potentially can be done here, but okay, we don't know how to do it yet. Okay, so the rate, let's start with the rate. Okay, so the rate, we do it by counting constraints.
Find the definition of rate.
Thanks. Yes, I will. Okay, so yesterday I should have said it a bit more generally. So what is an error correcting code? I guess more generally than what I am thinking about, you think of some space of strings, like all the strings in 0, 1 to the end. And a code should be a set of strings here that are pairwise far apart, so that the distance between any 2 points is at least delta times n. That's what we think of as an error correcting code. And the reason this is something we care about is because if you send a message and then there's some noise that happens, to make it be confused with another message, there needs to be a lot of bits that are flipped to move from here to here. That's why we like sets that are...
The balls around the points are disjoint.
Yeah, the ball of distance delta over 2 is going to be disjoint from the ball here. So if you allow it most delta over 2 errors, then they're the closest. So then, some errors occurred, and you really receive, I sent this, but you really received this. And then you find the closest white dot to your blue received word, and you're going to find the word that I sent. Okay, so that's error correcting codes on one leg. And what we're going to care about today, and most of the theory cares about, is a situation where these points are really a linear subspace. They don't have to be a linear subspace. It's just easiest to think about these objects. So it's just a linear subspace. So the code is just going to be some subset of 0, 1 to the n. This is, generally speaking, for us, n is the number of squares in the Cayley squared complex. Okay, so how many different dots do I have? So what we really count is the dimension of this linear subspace. If I took all the possible words, I would have dimension n. So we normalize, divide by n, that would be like rate 1. You don't need to add any more bits of redundancy. You have an n bit of message, you send n bits, no redundancy, also no error correction. If some bit flipped, there's no way to correct it. If we allow some redundancy, and that was like the huge insight of this whole theory, is that you can even send a little bit of redundancy and you already can correct errors, right? So the rate measures how much real information you have compared to the number of bits you're sending. So the rate is just the dimension of C as a linear subspace divided by N. Okay, so what is my rate here? So for us, C is at least let me say the number of squares. That's the ambient dimension, that's N in this notation, minus the number of constraints, number of linear constraints. So let's count. How many squares do I have?
G times A times B over 4.
G times A times B over 4, right? Because for every vertex, touching it are A times B squares. That's exactly this little picture. And I'm overcounting 4 times because every square is counted 4 times. Okay, and now what's the number of constraints? So I'm going to count separately for the A edges and separately for the B edges, because what are the constraints of my code? They're really exactly what's written here. That's the constraints. To belong to CA, you need to satisfy some linear constraints of CA. So maybe I should have emphasized, we are taking CA and CB not to be a subset, but to be a linear subspace of 0, 1 to B.
So it's G times A plus B.
Okay, so it's G. How many edges do I have of the A type? I have G times A over 2. And now for every A edge, I have B times 1 minus R naught. If let's denote.
Maybe you should say that CA and CB have rate R naught and distance delta naught or something.
Right, let me actually write that. So let's say that the rate.
We call it RA and RB that we even remember.
Right, but I want to.
Zero is fine, they have the same. What do you care?
Right.
What
At
do you care?
least-
They have the same.
Let me say that the rate is R naught and the distance is delta naught.
Wow.
She even said that you can assume that the
Same size. It'd be just easier for me. I don't want to worry about it. I worry about it. We worry about it in the paper. So if the rate is R naught, it means that the dimension of the space inside 0, 1 to the B is.
Simple question, stupid question. Dimension of C means just log 2, right?
Right,
Yeah.
right, exactly.
Or the number of linear independent vectors. Yeah.
Yeah, this log to the base 2 of the number of the words in C. I don't know how to denote it.
Really, you could do everything over a bigger field, right?
Everything, yeah.
And this is already assuming something about the generators, right? Like not having anything.
No, it's a lower bound of the dimension.
We haven't assumed
No.
anything about the generator.
Like in terms of some of the 4 cycles are not real 4 cycles, would that not be a problem for?
No, but at first you're going to take A's and B's such that they're not conjugates, so all squares will be non-zero.
That's still a lower bound.
Yeah, it still works, but don't worry about that. Like it's not a good thing to think about for the first time you think about these things. Okay, I'm not finished. There's still another term here, but let's just make sure this term is correct. So if the dimension of CB is R naught times B, means that it can be defined by this many linear constraints. And similarly, we have the symmetric thing. And you can see what Alex was saying. I could have written here RA and here RB and here RA, but let's not worry about that either. Okay, when you open this up, you get exactly 4. Okay, you get G A B over 4, and then here you get 4 R naught minus 3. Am I right?
Yeah. Yeah.
Okay, so if R naught is like 0.1, then this doesn't give me anything. I get something negative. So I haven't proven that my code has anything. But if R naught is bigger than 3/4, then we get something positive. Okay, so this is positive as long as R naught is bigger than 3/4. And if you happen to have seen the analysis for the 6-Spillman code, it's exactly the same, except you get R naught bigger than 1/2. That's what you happen to get. Okay, let's move to distance. Okay, so analyze distance. Let me tell you the Alon-Chang lemma. So here we're gonna require that the graph is an expander. So the Alon-Chang lemma says, not this Alon? Okay.
Sometimes called the expander mixing lemma.
It's not formalized exactly the same. Are you related to Chang? The way I heard this from Alex, I think it's a nice formulation, is that you have an expander graph. Let, I guess G is taken, let X be a lambda expander.
The H, but X is taken.
X is also taken.
But it doesn't matter.
Yeah. Okay. And
So that means that lambda is the second bound and the absolute value of the second eigenvalue.
right. Let me write H equals VE. Okay, and then suppose you have some set, a subset of the vertices such that the graph induced on this set, the graph induced on T has average degree. I should have said deregular.
Yeah.
It has average degree bigger than delta times D. Okay, so typically if you're on a vertex that belongs to T and you look at your D neighbors, delta fraction of them are inside T. And you move to one of the neighbors, again, delta fraction of them are inside T. Okay, so then T must be bigger than delta minus lambda times V. And this is an exercise to prove. It's really just writing the function that's 1 on T and 0 not on T, writing it in the spectral basis and calculating 1 line, 2 lines, something like that. And not
Maybe you want to call it delta zero.
okay,
Also the delta zero, the average degree.
thanks. Yeah, that's the hint, right? And so let's try to see why would this be relevant for proving distance. So the claim is that if the Cayley graph of G and A and the Cayley graph of G and B, so this is standard notation. It means the graph whose vertices of G and the edges go from G to A times G. Similarly here, if these are lambda expanders,
And the outside D.
okay, and okay, so what happens then? Okay, so okay, let's see what happens. If I look at a vertex G, I want to prove that then the code has distance such and such. We'll see in a minute. Okay, so how do I prove that the code has distance? I'm going to say, let's think of some word in the code, some function if that satisfies all of these constraints. And I want to prove that if it's not 0, then it must have a lot of 1s. So if it has a lot of 1, well, if it's not 0, it must have at least a single one somewhere. So let G be a vertex.
Wait, are we doing this trick again that we only care about 0? Because we're not.
Yeah.
Yes, it's a linear code. So
Yeah.
proving distance is the same as proving that there is no short word in the code.
if you don't like this trick, you should think of this way. Suppose we have two words in.
I like tricks. I just need to focus on that trick. So what I want to say that it's, if I have a word that is not on my code, it must have a lot of ones.
Yeah.
No, if you have a word in the code,
That
it's
is
not zero, then it must have a lot of ones.
Oh, okay. Okay, so it's like
Take two words and take their
it's
sum.
like
It's also
a minimal length of a lattice.
Yes.
Yes.
Yeah.
because you
okay.
can translate, that's why.
I'll still say what I wanted to say, which is, where's the picture that I drew with the dots? If the code didn't have good distance, it means that there were two elements in C, two points here that are close to each other. And now I can, instead of looking at the set of ones, blah, 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 I can look at the set of indices where they differ and do the entire argument. Okay.
If X and Y belong to the code, X minus Y also belongs to the code. So if
If they differ on very few bits, then X minus Y has very few ones. Okay. So suppose this vertex, it touches all these this matrix of squares. It sees some non-zero. One of these squares is non-zero. Okay. This one. Now, this because my entire function is a function in the code. In particular, on every G, the way this function looks on the link of G is inside CA tensor CB, right? So it means that, what does that mean? Every row belongs to CA and every column belongs to CB. So let's look at the column that belongs to CA. Since CA has distance delta naught, there must be at least delta naught fraction of ones here. And since this row belongs to CB, there should be at least delta naught fraction of ones here. So
Wait, why?
It's
Why?
not in the code.
No, but you know that one of these rows or columns is not zero because the SRF is not zero, but you don't know that. But
I started just with this one. Just one bit was
there's a
not
one there,
zero.
then that column is not zero. It has a one in it.
yeah, no, but you cannot pick a column.
I cannot pick a column, so I didn't pick anything in this picture. This is just one of the guys.
There is one column.
There is one column.
And there is one row.
There is one square that's not zero. Now let's see what that means. It means that this entire column of this one bit and this entire row of this one bit is a non-zero row and a non-zero column. So immediately it turns on these ones as well. Because CA had minimum distance delta naught and CB had, so already we have more than a single one on this thing. And in fact, it follows immediately just from the distance. It's known that if CA has distance delta naught, CB has distance delta naught, then the tensor code has distance delta naught squared.
Write it down.
So
Distance.
this, what?
Write it down with the distance. This is the sum.
Distance of CA tensor CB is known to be, well, it's equal actually. Delta naught squared times, well, okay, let's not normalize. So this is the distance. So it means that delta naught fraction of the squares are non-zero, but it's more than that. It just, for me, it's enough to say how many rows are not zero. Because of this row, at least delta naught of the columns are not zero, and because of this column, delta naught of the rows are not zero. So
The best you can do is to condense all the minimum number of ones that fulfills what you just said is to condense it.
Yeah, but
right, that's not what I care. I want to say
something
G has at least delta naught A
Non-zero.
non-zero neighbors. And when I say a neighbor is non-zero, a vertex is non-zero, I mean a vertex is non-zero if it sees some non-zero bit. So we started with one non-zero guy, and it already has a lot of A neighbors that are non-zero. And it also has delta naught B and non-zero. So this is like the A neighbors, and it also has many non-zero B neighbors. Okay, so if A equals B, blah, 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 it means that delta naught fraction of the neighbors of G are non-zero. Okay, so we define the set T to be the set of G's that touch some non-zero square. And immediately we get that the average degree of T is at least delta naught. So it means that the size of T is at least delta naught minus lambda. Okay, what does that tell me about the distance?
Wait, again. Can you repeat that again? How do you,
Yeah.
the degree of G?
What's the question again?
I
Just repeat the last
Just repeat.
argument.
Okay, so we concluded this, that so we set T to be all G's such that G touches non-zero zero square. Okay, define the set T. Initially, we knew that T has one element. Then we saw that whenever you are already inside the set T, it means that delta naught of your neighbors are inside T. And using the Elon-Chan lemma and the fact that this graph, that's the union of these two graphs, okay, I should have said that. If this is a lambda expander and this is a lambda expander, the union is also a lambda expander. So it means that I can use the Elon-Chan lemma and deduce that the set T that I defined here, AC, means that T is at least G times delta naught minus lambda. That's not yet.
Why not?
Okay, because the distance is counting the number of squares, and so far we only found the number of vertices that touch non-zero squares, but already we're happy because this is a linear number. So if we don't care exactly about the distance, it's already showing us that there's a linear number of bits that are on. Okay, but how many bits are really on? Whenever you are in the set T, you're touching all these squares. Your non-zero code were inside CACB. So your distance must be at least delta naught squared. So you get this times delta naught squared. That, okay, it doesn't really, I mean, I'm not going to care about this so much. Okay, so to conclude, maybe I just, here that the distance is at least delta naught squared times delta naught minus.
G went to the normalization.
Yeah. Yeah, I need to normalize that. Not really. Yeah.
The normalization is somehow linear in G.
Yeah. Yeah. Maybe I should start.
With G from the delta naught minus lambda and A and B from each of the delta naught squares. Doesn't matter.
No, I see.
Normalization.
Yeah. Thanks.
Okay, so these are
יש
the
פה שאלה.
So trying to understand, so did you like really use tensor code to get the distance?
not really. I mean, this argument is really just like the Sitzer-Spielmann argument for distance, specialized to this case. Don't need tensor code here at all. Right. So also another thing that maybe I should have said yesterday as well. In the expander code construction of Sitzer and Spielmann, you start with the base code and you rate you prove by counting constraints just like we did here. And distance, you have distance locally and use the expansion to lift it globally. And this is what we did here, right? We had distance locally and we used the expansion to the Elon-Chan lemma to lift it to global expansion. So far, it's the same. Now,
for the tensor code, you don't need any clever argument. It's just like when you have one row.
right. Now, the new thing here is that we're going to use the expansion also to lift the local testability. So now we're going to use the fact that the local tensor code has some special property we're going to discuss. It's locally testable in some specific way. And we're going to use the expansion to lift also the local testability. And that was not there before. Okay, so.
Irit, can I ask a question?
Yeah.
Yes, hi. I don't know if you can hear me. So I'm just trying to understand like this T there. So, but your G's are touching squares, they're not touching other G's. So how can you apply this Elon-Chan directly? You get this bipartite graph, right, between G and the squares.
Who is this again? I recognize. Shachar, thanks, Shachar, okay. It's annoying to me that I couldn't place it.
You didn't say explicitly that it's applied to the union of these two graphs.
So the way we did it was this, from the vertex G, we looked at all the neighbors of G, like A1 times G, A2 times G.
You're looking at the skeleton, the one-dimensional skeleton of the complex.
Right, and you're saying that because the local view at G is non-zero, it means that some of these rows are non-zero, and then for a row to be non-zero, it means that this guy, A times G, who's another vertex, is itself inside the set T.
But actually, it seems to me now, when listening to you, that for this argument, it's enough that only one of the codes has a good distance. You don't really need the other one.
Possibly, because you can only walk on that
Just like
skeleton.
you go along A and you ignore B, and the argument still works.
Possibly, yeah. Shachar, does that answer your question?
Yes, thanks.
Yesterday, I went to see the people on the screen.
So I realize from Shachar, I realize that we can talk also.
Yes.
That is the only thing that kept you silent till now.
Yeah, that's why I was silent. So first, I think it's good that both codes will be good, because otherwise, for one code, you get a very small distance, and then it will be 1 over D, which is for that code, and that could be too small.
But still constant.
Yeah, no, but you need it to be to compare it to lambda, and lambda is 1 over square root D, so you cannot allow.
But they're saying that you can use the Alon-Chang lemma only on the other, on the skeleton of this graph, and forget about this graph.
It doesn't matter.
Okay, it doesn't matter.
You're going to take CA equals
We're gonna need
CDF,
it.
and so.
We're gonna also need the distance for the local testability. I doubt it will work if the distance is trivial.
And one more comment is that you don't, so for you, bipartite expanders are good enough because you don't care about the most negative eigenvalue, you care only about the most positive. And that may be good because of those constructions of Ramanujan graphs, bipartite Ramanujan graphs for every degree, if you care.
But those are not algebraic, so how are we gonna get the squares?
What's that?
The way we get squares is because of some algebraic trick, right? Multiplying on the left and on the right. And if I get a combinatorial graph.
Yes, this is true. Okay, so but still, if you want, you could use bipartite ones.
Right. So there's this thing. Just to say what Noga was saying, there's this notion of one-sided versus two-sided expander, which means what does the lambda say? Does it say that all the eigenvalues are between lambda and minus lambda, or does it just say that they're smaller than lambda? So this is the one-sided. There's a weaker notion. It suffices for this level. Okay, there was something else I wanted to say. I don't know when, so I'll say it now. This construction of the left-right Cayley complex, it's not related to the local testability. I just want to say it. It's you can think of it as a quotient of the normal graph product. You take the two Cayley graphs, you take the product. What does it mean, a product? I guess you put one on the vertical, one on the horizontal. Your vertices are going to be pairs of vertices, and an edge is going to be you either walk on the horizontal component or you walk on the vertical component.
Cartesian product.
Cartesian product. And that gives you a square complex. But it's not good enough for us because it's not expanding enough for us. We'll see this later. However, if you now take the quotient of this thing and you say, I'm going to take the pair G1, G2 and kind of collapse it to the element G1 times G2. And you can check that an A edge multiplied from this side is going to still be an A edge, and a B edge multiplied from this side is still going to be a B edge. You get exactly this construction. So you can think of the construction as a quotient of the Cartesian product.
Can you do it geometrically without the group? The Cartesian product is okay. The product.
How would you take the quotient? This is a quotient.
That's what I'm asking. If you pass,
I wish.
you get a cube complex.
Tell me, I don't know.
And I'm asking if you have this.
And I want to have 3 graphs into the quotient. All open questions.
No, but I believe, I mean, I didn't check that carefully, but I believe that what you can present this is that you take as a Cayley graph, you take the Cayley graph of G cross G, and then you divide it by the action of G. And then you do the Cayley graph from both of them from the same side, but then you divide by G, the diagonal G, not the factor. And if you do it with G cross G cross G, and you divide it by the diagonal, you get G cross G and not 1G. So we really don't understand what to do in a higher dimension somehow.
No,
and we don't understand if there is really something really substantially the fact that the group is only 2 sides somehow. The group is left side and right side. There is nothing up and down.
but I'm even asking if
Maybe there is a trick. Avi suggested me some trick to go over this, but I thought about what you suggested me, which would be not completely transitive. That's, I think, the problem, but it's good approximation.
But anyway, it's
Okay.
a side discussion. But what did you want to ask?
No, I just trying to figure out if the way to construct it, you really need to get a group and talk about this, or you can, as Noga suggested, start with graphs and find a way to do this quotient.
Yeah, then you can take what these other constructions of expanders, like a zigzag construction, take a product, but then you need to find some way to squish it. Yeah.
So I think you control your time, but we want to see the analysis. So there are various potential extensions
Okay, sorry.
which are great. I mean,
But we still listen to the.
This is a yes and no. So if somebody gives you this graph with these properties to get to testability, do you have to mention the word group or just the fact that you somehow came up with this graph?
Don't need the word group. You need that locally, you are locally testable like a tensor.
But that's a combinatorial.
That you get, and you need some kind of expansion of a walk on the edges, which will see exactly what we need. And if you get that, you're happy.
Is there a characterization of these groups, of the groups for which the squares don't collapse?
Okay, let's talk about that at lunch. I don't know, yeah, okay. All right, so I want to now move to the local testability. So far, what have we seen? We saw that if the rates are not, is bigger than 3/4, and if delta naught has some relation to lambda. So we really only have 2 objects.
Some relation means it's larger than
Bigger than lambda. Okay, I just want to say, we started with a group G and 2 sets of generators. We wanted that this is a lambda expander. We also had base codes, and we wanted the rate to be high enough and delta to be larger than lambda. Once we had these things, we saw that we have rate and distance. Okay, now I'm going to add another requirement that the code C8 tensor CB, it's the code that we looked at here, is itself something, agreement local testable, we'll see in a minute, and then prove that assuming that property happens, there's also a parameter and some kappa. We want also kappa to be bigger than lambda, or lambda times delta, I don't remember. And then you get that the whole code is locally testable from the expansion. So let's kind of slowly start this. So really, let's start from what we want to prove, local testability. So the claim is that the code is locally testable. The formal claim is this: for every f in 0, 1 to the x2. So it's not a code, I'm just giving some string of the appropriate length. We want to test if this string is in the code or not. Okay? If it's close to the code, we're probably going to say yes. So we want that the fraction of times, the probability that we're going to say no is proportional to how far it is from the code.
A fraction of times for what experiment?
Okay, so what would be, so I need to say what the test is, right? So the test will be to select a random vertex G and to read the entire set of squares touching G and to see whether they belong to the tensor code C8 times C. So let's write it. So I'm going to write a reject of F. What is it? It's the probability that the test fails. So I'm choosing G at random from the group, and I'm asking whether F restricted to dot G dot. Okay, so that's exactly A cross B, right? I let A and B run freely. I want this to be in CA tensor CB. Actually, I want it to fail. This probability is the number of times that F fails the test. Okay, and you notice that this check, when you fix G and you look at this check, you only need to read A times B bits, right? So if you think of A and B as constant and G goes to infinity, then you're reading a constant number of bits. Like in Ehud's suggestion, you read 4 bits. You probably don't have an expander with only 2 guys, but okay. Okay, so what do you need to prove for local testability? I want to prove that the rejection of F is always bigger than kappa times the distance of F. Let's see. Okay, that's, if this holds, I say that the code is kappa locally testable.
Please try again.
Something went wrong. Okay. Okay, so the code C is going to be called kappa locally testable. If I want to add, I'll say with A times B queries. If for every F, I don't care if it's in the code, out of the code, for all Fs, the reject of F is at least K times the distance of F from the code. I mean, I should also say that when F is in the code, then the reject is 0, but this is true in this specific situation. Okay, so that's the definition of local testability. Use.
So just
Yeah.
when we're going to take something to infinity, it's going to be the set G, but we're going to fix the size of A and B fixed.
Yes.
Okay.
Right. Okay. Okay, let's see if I wanted to say something. Okay, so how do you imagine to prove such a statement? You're given some F, you start with some F, and you want to show that it satisfies this inequality. So what's the distance of F from the code? Well, there exists some F naught in the code that's closest to it, but you don't really have any algorithmic access to it. Like, how do I know what to say about this element? However, I have much more control over this thing, because if you give me F, I can look and see in which locations it fails the test, in which locations it doesn't fail the test. So what we're going to do is write an algorithm, we saw that yesterday, that starts from F and looks at the local views that are rejecting and slowly changes F, changes it, and hopefully gets to F naught, which is in the code. And then if you manage to do it, so there's going to be 2 options. Either you manage to do it, and then you're going to want to say that the amount of effort that you did is both proportional to the reject, and also it's proportional to the distance. You started from F, you reached F naught, the amount of changes you made is proportional. So that would—
to upper bound the distance if the rejection probability is small.
Right. And there's a possibility that when you do this algorithm, you get stuck, and you get stuck in a situation where you haven't reached a code word. You got stuck. And then we're going to show that if that happened, that can only have happened if you started with a function that was highly rejected, that the rejection probability was at least some epsilon 0 constant. And then the argument is like this. If the rejection was smaller than epsilon 0, then you prove the inequality. We will prove that the rejection is bigger of f.
Epsilon 0 is where, beneath that, you're not going to get stuck. That's the definition of epsilon 0.
Right. Yeah, the rejection of f is bigger than some kappa 0 times the distance of f to the guy you found, f0. And of course, this is at most kappa 0 times the distance of f from the code, because you found some specific code word that's close, and there could be an even closer one. Okay, and we also show that if, and this is standard in this field, if the rejection is at least epsilon 0, then kind of a trivial inequality can be written, because the rejection is at least epsilon 0. So it's at least, if you plug in here epsilon 0, wait, let me see if I got confused, right? The distance is at most 1. So the distance times epsilon 0 is at least epsilon 0. Okay, so if the rejection is epsilon 0, then trivially you get that the rejection is at least epsilon 0 times the distance. I guess, let me write it like this. Epsilon 0 times 1, which is at most epsilon 0 times the distance of f from the code. So that's kind of the structure of the argument, but let's now talk about the algorithm.
Algorithm is really a decoding algorithm. It gets a message which has some errors in it, and it tries to find the code word close to it. Given that there are few rejections, few inconsistencies.
So I'm asking it, epsilon 0, you know that if rejection is less than epsilon 0, you won't get stuck?
Yeah.
Okay.
Yeah.
So are you
We're going to prove it.
Okay.
Yeah.
Okay.
Yeah, we're going to prove it. So let's write what the algorithm is. Question?
Yeah, like about what Avi said, is this a decoding algorithm? Like, does this algorithm work for decoding?
Yeah, we'll see.
Yeah. Maybe you should write there over there in the case.
No,
Less
that's
than epsilon 0, prove that there exists f0. Prove that there exists f0 with this power, which is the algorithm will find. Yeah.
Yeah, because it's not just what's written there doesn't, it still could be not a decoding algorithm, because the second case, for example, could still happen if you are very slightly far from the code, right?
This case?
Yes, like just by what you wrote, it could be that that the rejection is very large, even if the distance is small.
I see. That's a good point, actually. I didn't think about that. But because of the regularity, that won't really happen.
Yeah.
What was the question?
He's saying that this proof just shows that if the rejection is small, you can decode. But he's saying it could be that the rejection is large, but the distance was small, and so you should decode, but you didn't. I mean, a decoding algorithm always says, if you're at a distance such and such, you must give me a code word. So that's it's not going to happen, but it's a good one. All right, okay. So the algorithm has 3 steps. First, there's like an initialization step. Okay. Want to take a break?
Yeah, it's up to you. We can take a 5-minute break when it's convenient to you.
Yeah, let's take one. Okay, so I'm going to write the algorithm. So the first step is for every, so input some function, some labeling of the squares by bits. Okay, so the first step in the algorithm is for every g, you let let's call it f sub g or wg, I don't know, f sub g, be an element of the code CA tensor CB closest to the local view at G. So that would be closest to F. Does this notation make sense? Think of the matrix indexed by A's and B's with these entries. That's the local view at the vertex G, and it might not be in the tensor code. Let's take some element in the tensor code that's closest. There might be more than one, just choose one. Okay.
This just choose one isn't going to affect.
I don't think so. I don't know.
Okay.
Yeah, we'll see. Okay, so now I want to do some loop, but to do the loop, I need to talk about the set of dispute edges. So if I think of the one skeleton of the graph, so just vertices and edges, and I have a G and I have a neighbor of G, G and AG. Okay, G has some local view, it looks like this matrix, and AG has some local view, it also looks like this matrix. But they share some squares, right? This square is going to be in the local view of G, and it's also going to be in the local view of AG. In fact, not only this square, all this book on this spine is going to be some row in the local view of G and some row in the local view of AG. And, you know, it could be that F sub G has some values on this row, and F sub AG has different values on this row. So either they agree or they disagree. Okay, so the dispute edges are going, what?
Disputed.
The disputed edges are going to be the pairs, where should let me write it here. That, I don't know, E star, these are the disputed edges, be all the pairs G, G prime in E, such that FG disputes FG prime. It's okay, this, I understand what I mean. Okay, so the loop is going to do this. For every G, it can look at all of its neighbors. It has A neighbors of A type, B neighbors of B type, and see how many guys it's disputed with. And then G can say, oh, maybe I can choose another local code word, something else in CA tensor CV. Maybe it's disputing less neighbors. And G will flip if that's possible. If G can go to some better code word, it will go. And once G did that, the cardinality of E star decreases by at least one. Right? The cardinality is at most the cardinality of E. And it can.
So this doesn't happen simultaneously for all G's. It happens for a single.
One by one.
Yeah. Okay.
So you look, every G.
Want to keep the closest property.
What?
So you started with the FG is the closest one, right? So
Right, that's the initialization.
when you change,
When you change, just do something that improves your number of non-disputed edges.
the closest property.
No.
So you're not changing just on the fact that, you know, closest could have more than one, but you are allowed to move away from.
Right, once you're finished here, from now on, through the rest of the analysis also, we're forgetting about F. What happened in the initialization step? You moved from one function F to a bunch, maybe you should think of it as a collection of F sub G's. So now you have like a bunch of local views. And these local views are no longer consistent with one F, right? Because they would have been, if your F was actually in the code, then all these local views would have been perfectly consistent and the set E star would be empty. But if that's not the case, these guys are not going to be all consistent. And from now on, we're forgetting about, well, sort of forgetting about F and only looking at this collection of local views and modifying it. So there's no notion of closeness anymore. Every G changes, how to write it.
To decrease the number of disputes.
Thanks, to decrease number of E star edges touching it.
Every G means in sequence.
In sequence.
Any G that can do it does it.
Okay, maybe if there's a G that can improve, improve. Then ask again, is there some G that can improve? Improve.
So you choose this G at random from all those.
No, we do some arbitrary order and you do it.
But you
Arbitrary order and you do it. And you loop. How many times can you loop? It's most E star times, right? Because every time E star decreases by 1 and it cannot go below 0. Right, so that's an upper bound on the running time of this step, this loop. And then the end part. Okay, so you finish the loop. No G can improve anymore. Two options. Either E star is empty. So if E star is empty, then
why is it clear that this loop ends?
Because each time E star decreases, so
Yeah.
it can decrease forever.
if E star is empty, then we define F star. F star, you need to define it at some square A, G, B. And you're going to do it by choosing one of the roots of the square, I don't care which one, let's say G. And you define it to be Fg of AB. So this is, there is some choice here. This may have led to different definitions, but the point is because E star is empty, all the 4 choices would lead to the same answer. So there is no real choice here.
Wait, sorry. I'm still not convinced why the loop must end, because the E star locally is going to decrease by 1, but can
Not locally.
No.
You're only
Change.
changing one at one point. You're not changing it all the G's simultaneously.
And you
Wait,
look
wait, wait.
at
But
the
can you-
overall thing goes down.
This is forget F. This is a collection of FGs. You're changing one of them.
Oh, so it doesn't affect.
No,
the
others are
other-
not changing.
The other edges that touches this square are
Yeah.
not changing.
No, the edges are now not disputed. Some of them are disputed, some of them are not. But the G's touching this guy are not changing.
You can remove touching it from the loop.
I see the point.
It just increases the number of E star edges.
Okay.
The point is that every vertex G
No, it's,
has one little square of its own. It controls it. It's your-
Now it's
it's
independent of the other.
Yeah, and
Yes,
it-
okay.
yeah, so, yeah.
Yeah, if it's independent of the other.
It's
then-
independent of the others are not
Yeah.
changing. So it can either reduce it or not. If it can, it does, and then somebody else who can reduce. Yeah, that's the point.
Yeah, we talk politics over lunch. I changed my opinion to agree with you. Okay, later on, you look around to your neighbors, see what their opinions are. You'll see that I already agree with you. So this edge has now become good. And okay, so the end, I want to define F naught to be for every square. I choose one of the 4 vertices that touches the square and take the opinion of that vertex to define F naught. Okay, so now for this square, since there was no dispute,
It doesn't.
means that all of these guys think that this square needs to be a 0. If this guy thinks it should be a 0, and this guy thinks it should be a 1, then this would have been a dispute edge. So since E star is now empty, there's no choice, and I just choose this value, and clearly I get a function F naught that agrees that locally it looks like it's in this standard code. So it must actually be in the F naught must be in the code, and we output it. So output F naught, which is in the code. Okay,
This you do for all square.
all G, A, B.
Now you define the code word.
No, so we've managed to find F naught. So if E star is empty, our algorithm succeeded. We found the code word. We don't know. I need to still worrying about how far is F naught from my original F. Okay, but at least we found some code word. If E star is not empty, it could be that, that's the more common thing in life. There are some dispute edges and there's no local move to improve. You're stuck and there's no, you're not in the perfect harmony situation. Okay, then you output stuck. And you're done. That's the algorithm. Now we can analyze it. we're really going to focus on the set E star. But let me just say, so we're going to follow this this kind of argument. We're going to say, we're going to show that the only way you can output stack is if the rejection is bigger than epsilon naught. So we're going to say that, okay, maybe it's a bit different. We're going to say this: if we output F naught, then it would be true that the distance of F naught from F, should have written it the other way around, times some K is at most the rejection of F. Okay. And why is this? Firstly, I want to say that the rejection of F is related to the size of E star. Okay, so let me not get confused with the factor 2. Just a minute. Firstly, we notice that E star divided by E is at most two times the rejection. Why is this true? If so, this is F, not the collection of local views. This is the initial F we got. If you look at an edge between G and G prime, again, it happens that G was not rejected, meaning the local view. When you look at G and all the squares of F around it are good, and also G prime is good, it's not rejected, then clearly this cannot be a dispute edge, right? Because they both agree with F. So that cannot be a dispute. So the only way this can be a dispute edge is if either this guy or both
Have to
are
change
rejected.
their,
Right.
and they change only if they contribute to the rejection.
Exactly. So it means that the size of E star is roughly like the fraction of rejecting vertices. Okay, good. So now all I need to show is that the size of E star, it also upper bounds the distance. Because then I get this inequality. The rejection is bigger than some constant times E star, which is bigger than some constant times the distance. Okay, so now let's look at two sets. G naught, which is all the vertices that reject initially. So let G naught be the set of vertices such that the local view F at G not in CA. That's the set of guys that initially their local view wasn't a proper thing. And G1 is going to be all the G's that algorithm changed at some point in the loop. So at some point while the algorithm was running and the loop was looping, this G decided to change its value.
Algorithm change F sub G.
Changed F sub G at some point in the loop. Okay, so firstly, G1, since the loop is only running E star times, G1 has size at most E star. Okay, what about G naught? G naught is exactly, the size of G naught divided by G is exactly this. Okay, so again, so it's bounded by this, it's equal to this. So both of these guys are bounded by some constant fraction times the rejection probability. I'm not doing the constants, it's too difficult for me. But so the size of G naught union G1 is at most some constant times the rejection rate. Now I want to claim that every square that does not touch, so a square touches 4 vertices, every square that doesn't touch any of these guys, F naught is equal to F on this square, right? So the distance between F and F naught is bounded by the number of squares touching these guys. So, you know, you need to multiply by A times B because that's the factor of square. You have more squares than you do vertices, but it's some constant. So we're using here really, it's important here that A times B is a constant compared to G, which goes to infinity. Okay, so we proved this.
This constant K is not the kappa that you talked about, so it may be C or something.
Okay, yeah. I'm really not going to be able to do the constants.
Is it clear that F0 that you got is in the code?
Yeah, it is clear because when I outputted F naught in this algorithm was only because E star was 0. When E star was 0, it means that I have a collection of local views that are all agreeing with each other.
No, but they also.
They also
Right.
require to be on the tensor code, so they are.
No, but that was your question from before. You initially
No.
you asked them to.
No, you always, at every step, every local view is always in
The
the.
question is whether
That's important. The local view
Always in the.
changes to something else inside CA tensor CB. The local views are forced to always be inside this thing.
Okay.
Right. Okay. So what I need to prove now, so we saw that if we actually output the algorithm found F naught, then we satisfy this inequality. And now I want to also show that if we output stack, then actually E star is bigger than some epsilon constant. Some constant. Formally, there exists some constant epsilon naught such that blah, blah, blah. Okay, this will be good enough because of that reasoning that we said here. Okay, because we said that the number of dispute edge is a lower bound on the rejection, so it means that the rejection must have been large to begin with. Okay, so that's.
How do you see that there's some constants at that?
No, I'm going to prove it. That's not trivial.
Okay.
Okay. So this is really my main goal to prove that if I get stuck, means that I ran the algorithm, every G locally cannot change its value to be in more agreement. I'm going to show that it must be that there's a lot of chaos, a lot of disagreement. Okay. Okay, so let's keep in mind, so this is like our graph. This is the graph. So the vertices are these G's and we have edges for the A's and the B's. And we have some edges that are in E star. These are red edges. I don't know, maybe there's only a few. Okay, but we're gonna now prove some kind of properties on them that they resemble what we did for the distance. And we're going to use the expansion to show that if you have one red edge, then near this red edge, you have another few red edges, and then you have more and more. And then using the Alon-Chang lemma, the red edges are everywhere, meaning that the fraction of red edges is at least epsilon naught. Okay, but this argument is going to fail if we don't assume the local testability of the local tensor code. So now we'll see where this comes in. So let's try to do the argument before without doing any assumption, and we'll see where we get stuck. Okay, so suppose I have some red edge, meaning an edge in E star. So it means that there's some G here, some A times G here, and the local view of this guy and the local view of this guy are different. So there's F sub G and F sub AG, and this is a tensor code word, this is a tensor code word, but on the column that they share, they disagree. So if I draw the book, these are the squares that they share. So what does it mean that you have here a code word of CA tensor CB and here another one, and they disagree? It means that there are a lot of different squares in which they disagree, delta naught. So these are two code words on CB, and they disagree. So they disagree on delta naught fraction of point.
Again.
Because of the distance of CB.
Right, so this is in CA tensor CB. In particular, when you look at this row, these squares must be in CB. This is also in CA tensor CB. So when you look at this row, it must be in CB. So these are two different code words in CB. And the fact that this is a dispute edge means that they're not the same code word.
This book corresponds to a row in the tensor matrix.
Maybe.
You can see that there's somebody there.
Yeah, but
And this
There are two different matrices.
So here's the matrix for G, here's the matrix for AG. There's one of the, did I say row? Let me do it a column. This column, these squares are exactly these squares.
one correspond to A.
And maybe some other column in AG, these squares correspond also to these squares, but from the local view.
Variables.
Okay, and the question, and all the other squares here are different. There's no other square that they share. But here, this is a code word, this is a code word, and if they disagree, it means that they disagree on several places. Okay, so these are all zeros, say, and these are all ones. I don't know. Something. Okay. Okay, let's look at one of the squares.
She's using the fact that CB has a distance delta 0. So
Right.
if two code words are different, they're
Oh,
different
yeah,
in a
no,
lot
okay,
of
okay,
places.
okay. Thank you.
So let's look at one of the squares. G thinks that this square should be 0, and AG thinks that it should be not 0. If we're over binary alphabet, 1, but otherwise, just two different symbols. Okay. What about this guy? What does he think? Okay, so this guy is, I guess, G times B, and this guy is maybe A times G times B. So I'm saying that either this edge is an edge in dispute, or this edge, because they cannot all agree because these guys disagree, right? So I must have either, for every red edge here, I must either have either this guy is going to be in E star, or this guy, or maybe more than one, but at least one of these three, right? And also, for delta naught of these squares, the same thing happens. So you already see some propagation going on. But here's my problem. It would be nice that already this implies propagation and we can finish the argument. But the problem is, it could be that all the time when I look at all the dispute edges, they always happen to be incident on one vertex. So for this square, maybe you choose this edge to be in dispute. And for this square, maybe you choose this edge to be in dispute. And for this edge, this square, and here. And so now when you move, say, to discuss this edge, you say, okay, now I'm going to do the argument again, but from the point of view of this edge.
But once again, you choose one-dimensional edges that touch G. So you're all the time staying.
Stuck at G.
It's like a small
Right.
click.
I just want to say there are all these, now there's different book, right? It's a book on this edge. But still, so, again, you can say maybe this one is in E star or this one. But really the one that's going to be chosen is the guy that touches G. So you're never escaping an edge that touches G. Might be the situation where you're at G, all the edges touching G are in E star, but that's it. You cannot argue about anything further. And so that kind of, you want to say that makes sense because maybe it means that there is some local problem for G. Maybe that means that G needs to change. It disagrees with everyone, right? It must be something wrong with this guy. So let's just fix G and everything will be fine. Okay, so let's now look at this property. How does it look from the point of view of G? With this picture. Okay, so this is the point of view of G. And so G has these neighbors like A1, A2, and A3. And A1 tells G on this row, you need to look like this. A2 tells G on this row, you need to look like something. A3, similarly. And the B neighbors also, they have their opinion about what G should think. B1 thinks something, B2 something, and B3 something. Okay, so basically, from the A neighbors, G gets a bunch of rows. From the B neighbors, G gets a bunch of columns. And okay, so there's two options. Either these guys all agree with them, between them, okay? So, you know, A3 agrees with B3, with B2, they all agree. But somehow G doesn't agree with any of them. So G had some other opinion. Well, if they all perfectly agree, then you have here really a matrix that, you know, all the rows are in the A code, all the columns are in the B code, and there's one single matrix. So clearly G knows what to do. It can change to the whatever its neighbors think, and we're happy. But that's not really the case, right? Because we didn't say that G disagrees with everyone and all of them perfectly agree. It might be that most of the neighbors of G agree with each other, but some of them are in dispute. Every time neighbors of G are in dispute, it's somewhat of a good thing because it means that you can, I don't know how to say it in the picture. You're at G. These edges are a dispute between G and other guys. If two neighbors of G are in dispute, it's already an edge that doesn't touch G. So it's already, it will give me a better propagation. So I'm happy when I see some edges further away that are in dispute. I want to say that if G disagrees with a lot of its neighbors, it must be that a lot of them themselves disagree with each other. That's what I'm aiming at. If G disagrees with a lot of people, then they must themselves disagree with each other. So what's the contrapositive? I want to say that if most neighbor pairs agree, I'll write it mathematically in a second, then G could have flipped.
We won't be stuck.
Right, we wouldn't have been stuck. And okay, what does if most neighbor pairs agree? Really what we have here, and now I'm going to say some property of tensor codes that has nothing to do with this construction. From the A neighbors, I get a matrix that is, all the rows are in the A code and the columns I know nothing about. That's one matrix from the A's. From the B neighbors, I get the other thing, a matrix whose all the rows are in the B code and the columns I don't know anything about. I have these two matrices, and every time I choose a random A and a random B, whether they agree or not is really just determined by what they say on this square. Either they agree on this square or they don't. Okay, so I can count what fraction of times when I choose a random A and a random B, these guys agree. Okay, and that's some number, and a code is going to be, a tensor code is going to be called the agreement testable if the fraction of disagreements here is an upper bound on the distance of both of these matrices from the tensor code. So I'll write it formally.
So now this is going to be an additional property we're going to add to CA and CB.
Right.
In order for this.
Oh.
Right.
Yeah.
It's exactly true.
So you have to pick the code CA and CB.
Such that
something happens.
Oh, so it's not for every CA, CB.
It's not for
every
So what's this property? So let's say that CA, let me now call it, instead of A and B, which is difficult for me, let me call it columns and rows. And CR is, I don't know, some parameter agreement testable if for every pair of matrices MC and MR. So now what is MC and MR? MC is a matrix such that the columns are in C and the rows I don't care about them. And MR is a matrix where the rows are in R and the columns I don't care about them. So you give me two matrices and I say that the probability for choosing a random index I and a random index J that MCIJ equals MRIJ. And so I look at these matrices and I look at the set of indices where they disagree. Okay, that's exactly this. And this is bigger than some K times the distance So I want to say like the distance of this guy from the tensor code, maybe to be symmetrical, I'll say the average distance. The distance of M R from C tensor R. That's okay. I can also say, and also bigger than the distance C tensor R. So that's going to be our definition.
So maybe you want to say that this is an example of a local tester for a tensor code.
There's some transformation you need to make here, which I thought to skip. That's true. It's equivalent to saying that the code, the C tensor R, is locally testable by choosing either a random column or a random row and checking if it's in the appropriate code.
Mhm.
But there's some step here that I don't want to do. It's like once you know what to do, it spells itself out. There's nothing clever in this step. But, I want to get to finish the analysis. So
How big should K be? So sorry, I'm asking from far away. So K should be a constant here, independent of degrees of the
Yes.
size of the code.
So Noga is asking what is K here? It's suspicious. So that's actually true. K cannot depend on any of the other parameters. So if you think of the dimension of these matrices, although we, in our construction, we're thinking of these as constant, but still they're not really constant because lambda will depend on these sizes. So you should think of the size of the matrix as something that can be large as you want, and K will be a constant independent of that. K will depend on delta naught, the distances of R and C. Okay, but not on the dimension of the matrices. I mean, what I mean will depend, I mean, in the constructions that we know, in the codes that we know that satisfy this. So brief history, tensor codes and whether or not they're testable also kind of goes back to, we think of maybe polynomial codes on the rows and the columns. These are like bivariate polynomials, and they were studied a lot. And then Ben Sasson in Sudan said, let's look at it in a more general question. What if we have some arbitrary codes? We look at the tensors. Is it still going to be testable? And they were able to prove that for tensor of 3 codes and more, you can get testability. But somehow for 2, the proof didn't work. It looked strange. And maybe the proof should also work for 2. But then Paul Variant found a counterexample. What did he find? He found 2 codes, C and R, and 2 matrices like this, such that the matrices are quite close to each other. But so there's a matrix that's close. You can fix the columns or you can fix the rows, but you cannot do it simultaneously. So kind of, if you take the average of the 2 matrices where in this area of disagreement you choose in some way, you'll never get to a code word. Okay, so that seems to say that this does not hold in general. So there are codes C and R such that they don't satisfy this property. But then in work with Avi Vigdalson and Madhu Sudan, we managed to show that if one of the codes has some property which we call smoothness, then this does work. So if C is smooth, then this does work. And Ben Sasson and Widerman even slightly refine this notion, something they call weakly smooth. And for example, random LDPC codes are smooth. So you can choose C to be a random LDPC code, and then you have this property. And the K doesn't depend on the dimension, it depends on the degree of the random LDPC code. So I'm not going to get into the details. Just let's say for now, add this as an assumption on our CA and CB.
So there are explicit codes with this property?
So we're going to use these codes on a constant, right? On a set of size A. So random LDPC will be explicit once we find it. You can also take other situations, like you can take read Solomon code tensor 3 times, it will give you, okay. I mean, okay, think about it as some constant size problem. If you know it exists, then you can search for it. I guess I don't have any place to write down that we require this from CACB. to be kappa locally testable. So I guess we're gonna say this is true, assuming CA tensor CB is, I don't know, kappa prime agreement testable.
Do you know if the condition is necessary? Can you falsify the lemma with other things?
I would imagine, but I'm not sure. Possibly. Yeah, possibly. Okay, so let's go now and finish the analysis. Okay, so remember where we were. We said we have some set of disputed edges, and we want to show that this.
So in our setting of G and AG, and then the two squares that you draw there, what would be the MC and MR?
Oh, okay, good question.
The matrix of G and the matrix of AG.
No.
No.
If you're at a vertex G,
Because otherwise the distance from the code both is 0.
right, if you're at the vertex G, then G has, influences from the A neighbors and influences from the B neighbors. The A neighbors are going to be MC and the B neighbors are going to be MR.
So each neighbor give him a row or a column.
Right.
We collect these guys, we collect these guys. So these don't need to agree with the code.
Right. The collection of A neighbors doesn't have to be column-wise anything. And the collection of B neighbors doesn't have to be row-wise anything. And now we see how well do these neighbors of G agree with each other.
This is the collection of disagreeing neighbors A and disagreeing neighbors B.
No,
Other
any,
neighbors.
all of the neighbors.
Okay, let's maybe that's a good way to think about it.
So far it doesn't depend on the A. It's not
Yeah.
defining this was just for G.
Yeah, you have MC and MR for a specific G. The problematic one that we draw here.
Right, so this was our motivation, but now I tried to kind of go back and say, okay, let's do the argument all over again. We start with some set A star, we don't know how big it is, we want to prove it's large, so first we drew it, maybe it has one edge only. Then we saw that if you already have one edge, some more edges must also be in E star, but it could be that a lot of them are adjacent on one G. So really what's going on is that once you fix one edge in E star, three things can happen. Either a constant fraction of the parallel edges are also in E star. That's one event that for me would be a good event. Or either G or AG has somewhat of a high degree inside E star, like delta naught over 3. So either G has delta naught over 3 neighbors in E star, or AG has delta naught over 3 neighbors in E star, or this edge has delta naught over 3 parallel edges in E star. Does this claim make sense? Okay, so what is a parallel edge, by the way? For an edge, choose a random square containing this edge and move to the parallel edge in the square. So you see, this is like a two-dimensional walk, right? It's a walk on the edges. It's not like going from vertex to vertex. You move from an edge to a parallel edge, da, 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 da. Notice also that this walk is pretty expanding, right? Because you move from G, AG to an edge, GB, AGB. So if you look even at just at this endpoint, you move from G to GB to GBB prime. You're really doing a random walk on the Cayley graph GB, which is an expander. So you're gonna mix pretty well, not all over the place, because you're always going to stay at an edge that has the type G, little a times G. So really you're mixing on a connected component of the set of edges. For every edge, you can think that there is some label. The label is the generator that moves you here or back. So a label is like a pair of generators, A and A inverse. And the parallel walk never changes the label. Okay, so it has a few connected components, but few.
Just the size of A.
Just the size of A and or B, right? If you're on a
Well,
B edge,
yeah,
you'll stay on
for
a B
this
edge.
example, for A, yeah.
Right. So how many connected components do you have? A plus B. And each connected component is huge, it's linear. So if we manage to show that a good fraction of this component is in E star, it's a linear fraction. Okay, so to summarize all this, if we happen to be in a situation where when we start from an edge in E star, we move to a random parallel edge, we stay in E star with some probability, I don't know, delta, then it means that the size of the set of E star is at least delta minus lambda inside this connected component. So that's already fine. We found a linear number of E star edges, and this will be our epsilon zero. So that's already fine. I should have even said that before we talked about this whole business. But it could be that it's not happening. When you have a E star edge, only very few of the parallel edges are in E star. And really all the E star edges are going to be here, touching either G or AG. So then we need to look what's going on here. And we see that, suppose it's G, means that a lot of the neighbors of G are in dispute with G. In this case, we'll show that the neighbors of the neighbors must have a lot of dispute. I want to show that many neighbors, so here's one neighbor of G, here is another neighbor of G. We're going to show that these two edges must be in dispute, either this one or this one. So let me draw a better picture.
הלוח הקודם תראי מלמעלה.
Have an edge between G and AG, but now I'm forgetting about this edge, and I'm really noticing the situation where I have many neighbors of G that are in dispute with G. And I want to say that now I'm going to define MC and MR. MC will come from the A neighbors, A1G, A2G, and so on. That will give me MA. And GB1, GB2, oh, I could do it wrong. This is A1, A2. This will be MB, this will be MA. So all the B neighbors of G are going to give me some MB. All the A neighbors of G are going to give me some MA. And now I can ask myself, let's choose some random neighbor of G, this guy, and some random neighbor of G, this guy. So one B neighbor, one A neighbor, and ask ourselves what happens to the square, to this square. So this square gets one bit from G, one bit from each one of these four vertices. And do they all agree on it, right? So the bad thing that we were afraid of is that, maybe G disagrees with its neighbors, but the neighbors agree. All the neighbors know what this value should be. If that's the case, it means that MB and MA agree on this bit. It's exactly the situation we were testing here. It was like MA at location A, B, and MB at location A, B. And we were just asking whether they agree on this coordinate. Okay, so if all the neighbors, if many of the neighbors agreed, it would mean that G has a value that it could have flipped to that would agree with a lot of its neighbors. But we know that G.
Again, where do you quantify the number of neighbors?
Okay, so in my messy picture over there, we said that either delta naught over 3 of the parallel edges must be in dispute, or either G or AG, let's say G, has delta 3 over naught fraction of its neighbors disputed neighbors. So a lot of them are in dispute. Okay, I'm saying that this means that a lot of the neighbors not only are in dispute with G, they must also be in dispute among themselves. Why is that? Because if they weren't, if almost all of them agreed with each other, then by the agreement of stability, there is a value that G could have chosen that would be in much less dispute with its neighbors. Okay, so it's really like this definition was exactly made for this argument. And it shows that if G has a lot of E star neighbors, then in the roof of G, I can define the roof of G to be exactly these edges, the edges closing squares that touch G. There are going to be many, a constant fraction of edges in the roof of G that are also in E star. Okay, so let's write this as a conclusion. So if G touches many star edges, when I say many, I mean a constant fraction of its neighbors are in E star edge, then many roof edges are in E star. And the roof edges, right, they're far, they don't touch, not this guy and not this guy, right? Okay, maybe one of them touches AG, but that's it. So that will give us the propagation. I mean, I don't think it will be useful to write it formally, but what happens, you have some kind of a random walk. Okay, so let's just describe the random walk. We reach some kind of random walk on the edges. The random walk says, you know what? You start with some edge. With probability, something, whatever, you can optimize the constant. Let's say with probability half, you go to a parallel edge. With probability half, you do something else. What's the something else? With probability half, you choose one of the endpoints. Okay, we choose this, and go to some roof edge. Random roof edge. And okay, so we define now this random walk. You can describe it in some, as a, you know, in some. So M is like some Markov chain on the edges, and you show that if you look at the function 1 E star, okay, it's a function on the edges that's 1 whenever the edge is in E star and 0 elsewhere. And you look at this. Okay, I didn't use this notation before. So really, what you're thinking of, you have a graph whose vertices of this graph are the edges, and the transition from edge to edge is according to this random walk we just described. And on this, you apply the Alon-Chang lemma. So basically, you show that the set E star induces a subgraph with a large average degree, with large probability to stay inside the set. You start from a set in E star, you go to a random edge on the roof, and with some constant probability, you're still in E star.
So before that, you want to say, before E star and anything, you want to say that you're defining a new graph on the edges.
On the set of edges.
Which is expanding.
Which is an expander.
Yeah, that's great. And then once you have it, then you can apply that Alon-Chang lemma.
Exactly. Of course, you get a weighted graph, so you need to have an appropriate version.
Yeah.
Probability.
So the expansion of this new graph, the expansion of this new graph follows from
the expansion of the Cayley, the components, the Cayley graphs. As we said, for the parallel walk, you can see that so this random walk has two components. Probability half, you do a parallel walk.
is just a copy of
the Cayley graph.
Yes.
Maybe it's folded in half, but it's a lambda expander. Each component is a lambda expander.
Is there two different random walks, right?
Your random walk is like a convex combination of these two things.
Okay.
Because you don't know which one will be bigger
Oh,
than
okay. I thought we treat each one of them separately. You treat them both together.
Doesn't matter.
So you have two different edges on your new graph. One
Right.
is go parallel, and the other one go to the roof.
Exactly.
So this goes
Go to the roof of you first move to a vertex and then to the roof of that vertex.
So why does the go to the roof have expansion? What does it follow from?
So here you probably need both of the initial graphs to be expanders.
So I can show you. You can do it like this. You define a You know what? I'll show it to you offline. It's if you want to just get an intuitive feeling, when you were in this edge, you move to G, and then you moved either to an edge that touches GB, some B prime and A double prime, GB prime. So you see that at least one of the Cayley graphs kicked in. Like at least one time you really moved according to a lambda expander. Okay.
So
You can, the way the kind of the formal proof goes is you decompose this Markov operator by doing a down, you do a down operator, then you do one walk in the Cayley graph. So either you were on an edge, down moves you to a vertex. Now from the vertex you walk according to the Cayley graph, either to a B neighbor or to an A neighbor. That's already gotten you a lambda. And now you're doing up, meaning you moved from a vertex back to an edge. Okay, and the down and the up are, what do you call it?
Projection.
No.
A joint.
Thank you. Joint, so it works out. It's actually not a difficult analysis.
So, say again, the down and the up are what?
So you got like a down, a Cayley graph, and then up, and then you need to analyze this thing. But since up is a joint to down, you get this is equal to MDF DF. The up from here moved to a D here because they're a joint. And then so this is now a function on the vertices. It's the same function, and this is an expander. So immediately you get that this is.
So here you do use the fact that here you do need the separate expander property of each of the Cayley graphs.
Okay, great question. Yes. So I assumed here, for example, that A and B have the same size. In that case, you probably it's okay to also assume that the union is an expander. But if you want to say have one set A to be, I don't know, D squared and one to be size D, suddenly there's some imbalance, and the right thing is to weigh them, to make them have equal weight. And then for this analysis to work, you need each one of them to be a lambda.
But the answer to him, he didn't care about different sizes. For same size, you need both to be expanding.
Do you? Don't you need the union to be an expander? I think it might be enough. Okay, I'm not sure.
Because if you do, yeah.
I'm not sure. It seemed to me that maybe this M in that case is the union of the A and B walks. But
That's interesting.
Oh, I see. Because it was either a random A neighbor or a random B neighbor.
right.
Maybe.
Yeah.
So so it might be that if A and B are of the same size, in all of the proof, you just need the union to be expanded.
I see. So you're saying maybe it's interesting to choose something that's not an expander. Okay, I didn't check it, so I don't know.
In order to get what? Not why?
No, maybe it's interesting for some other reason, maybe even for getting more symmetries. You can have A and B to be some kind of billion-like thing.
So A and B will be smaller, like if you just need the union to be.
Right, okay, but not promising that maybe this is nonsense. I don't know. Okay, so good. So we reached almost the end. What else I wanted to say? Okay, let me just say something to summarize. Not talking about how, so okay, so we got this scheme, this code scheme where you plug in a group into generating sets and two codes, and you get a definition of a code. And we said if you assume some more properties in your components, you get some properties in your resulting code. Now, if we want to prove that there exists error correcting code with constant rate, distance, and locality, we need to actually instantiate it. We need to actually come up with base codes that have good rate and distance and satisfy that thing, this agreement testability thing. And also we need to come up with a family of groups that G goes to infinity, but A and B stay fixed. And also there's this no squares collapse, non-conjugacy condition. Okay, I'm not going to talk about the details of that. I just want to point out one thing that I think is interesting, and that really what you have here is a two chain, right? From vertices to edges to squares. We also saw it on the slide. So we have here the squares. It's like a tripartite graph. Right, so these are the squares of the complex, and then each edge participates in some number of squares, and then each vertex participates in some number of edges. And we used in a way that I don't know what's the best way to articulate it, some kind of expansion properties. So there was, of course, the random walk that goes from vertex to edge to vertex. We also used a couple of different random walks that go from edge to square to edge. And the expansion of these two things combined with the code somehow gave us the properties for the analysis. And we also talked about yesterday that there's so here we put the bits, here we put the constraints. Here we put, I called it the dependencies.
What's the dependence?
Between the constraints.
Between the constraints. So
It's a
the link
tensor.
of every vertex, you saw a tensor code. And in a tensor code, if I had more time, and I'm not complaining, I was given a lot of time, and I would have been able to prove why, for example, random LTCs satisfy this. You would have seen in the proof how we use the fact that tensor code has some kind of dependency between the constraints, right? If you satisfy, suppose you have a 3x3 tensor code. If you satisfy these two, and then also the third one, then the last row should also. Right, it's exactly like a magic square. So really, it boils down to these magic squares on the tensor codes that are some kind of dependency between the constraints of a tensor code. And like the first original locally testable code is the Adamant code proven by Blum, Luby, and Rubinfeld. And there the analysis is exactly using the magic squares. So there you have the bits are like elements in 0, 1 to the n. And the constraints are triples of the form x, y, x plus y. And the dependencies are these magic squares. I'm not going to say what they are, but when you prove that the Hadamard code is locally testable, you make use of some kind of dependencies between the constraints. Essentially, it's the x, y, x plus y, z, w, z plus w, and then you sum up these verbs like x plus z, y plus w, and then the summation of the four things. This gives you a magic square. So if these are satisfied and two of these are satisfied, the third one should be. And that means that if you violate a few of these triples, because of the magic squares, more are going to be violated and more. That's not how the analysis looks like, but it really is. And so in some sense, it's the same as this.
In a way, this is the advantage of multiplying from the right and left because they commute with each other. So even though we are in a situation of something which is very non-commutative, there is a corner of commutativity which enable you to do a kind of a magic square.
This is not necessary because the magic square analysis and the homomorphism testing works in non-commutative groups just as well as it does in commutative groups. The Blum-Ruby-Rubinfeld analysis works also in non-commutative.
We should talk about that. We didn't manage.
No, I'm just saying this is not essential to that story of Blum-Ruby-Rubinfeld. Homomorphism testing of groups works in the non-commutative setting with the same group.
I know, but it's okay. The point that I was making is that we try to work before we got to this capture with the squares, Ramanujan square complexes, we come from quaternions that you have like two sets of generators, elements A and B, exactly the same, but we have very few and short relations AI Bj is equal to Bj prime AI prime, you know, like all the relations are only like that. And somehow we got stuck because we really don't understand if we got stuck just because it was too big. Or we got stuck because of something essential that we couldn't really label the edges in the same letters up and down. And that's amount basically to say that when you look, you have an edge, the edge look on its link, right? But if you look from one side of the edge, on the other side of the edge, it's different. While here, it's the same way. The vertex thinks the same.
This is a much better argument for commutativity. It's not the analysis of the magic squares, but just the labeling of the edges in a consistent way is the argument for commutativity.
That's a serious.
If you had a way to, now thinking, I'm just thinking because I don't remember. I remember that you guys work on this non-commutative BLR, but maybe if you had a way to resolve it, it can help us here because
I think the labeling, the fact that you are talking, you know what you are talking about, what are the elements you are. The naming is central. Yeah, anyway, I think that. Anyway, that's speculation. So
is it possible that this could work with both sets A and B acting from the left from the same direction, just with some extra conditions on A and B?
Well, you need to close the square. So for example, if you had this situation, you're multiplying all the time from the left. But if whenever you multiply by B and then by A, there's a way to flip it and multiply first by A prime.
You need some condition on A and B so that for every element there's a so that you could.
But that's not enough. So at first we thought about square complex, so we thought, wow, that would be fantastic. But then the problem that Alex mentioned showed up that even if you manage to close the square, and there are Ramanujan constructions of this form, you still need to be able to label. So an edge, from the point of view of one vertex, needs to label its squares in some way, and the labeling changes when you move to the other point of view.
But there's no obstruction saying that there wouldn't be some nice group and some choice of A and B such that you multiply from the left and it all works out. It might.
There's no obstruction.
There's no obstruction saying that you have, because this will give you a transit.
not commute with each other unless the group is commutative, but then it's not an expander.
No,
if A and B generators and they commute with each other.
They don't have to commute, right? They have to have some property that you can switch.
Okay, maybe
Pick a different element. But then this will give you a transitive.
I see. That's why you're thinking about it. Yeah. Yeah.
I wonder if you worried, you probably didn't worry about it, but I wonder, did you try to check what kind of numbers you get? So suppose I want distance and rate 1/1000, what would be the locality? Would it be more than 1 billion?
So actually, I'm interested in this. So if there's a student out there that's interested in working on that, I'm happy to. I think it's interesting. Yeah, I don't know.
But just plugging in what
It's very explicit. It's not really.
So like it seems like everything was polynomial, right? You didn't.
Everything is linear. Yeah.
No, like in terms of like the
relationship between the parameters is polynomial. Yeah.
Right. Yeah. No, but no, it's a good question, right? Suppose you want something.
Because you square A times B is pretty big. A and B have to be big for the codes, and then the square of them is a locality. I mean, A times B.
Right.
So yeah, just wonder.
Just say A times B doesn't have to be the locality. This was a comment Zev made yesterday.
Right, yeah, maybe not.
You can choose an edge and just read the squares along it and ask if it's in the appropriate code. That would be a good test. You lose some factor in the soundness. I just wonder if this can be made like a feasible code, right? That would be great.
Another question, it is, as we said before, it seems like your decoding algorithm doesn't work up distance delta over 2, but up distance something like delta over A times B.
Mhm.
So this is also a question.
Like what's the distance where you can prove you can decode?
Yes.
Yeah, that's a good question. Also in the Cipher-Spielmann codes, which are simpler, we don't know how to decode from distance delta over. Well, there the distance is like delta squared. You would expect to decode from delta squared over 2. Actually, I think we do know how to do it. The zero analysis that people are usually familiar with does delta not over 4. But I think it can be improved maybe by things like Fernando is doing. So I don't know.
Do you want to tell us what G, A, and B use, or?
Yeah, Alex can tell us.
What?
What is G?
What will be?
What is G, A, and B? A, B, and G, N.
Okay, so you know, we have many examples but nowadays of Ramanujan Cayley graph. They only
Ramanujan doesn't.
it doesn't need, right?
Yeah,
I mean,
you have many algebraic expanders. Yes.
what needed a little bit of thinking is, well,
No, but you need
not
something about.
so much thinking, but looking at the package, you know, from old works.
But you need that CA tensor CB.
That's
That's
CA and CB are codes, and these are graphs.
Right, no, but
don't
you-
care. You only need the size of A and the size of B.
The only
They don't talk to each other.
No, the
The
only
rules
thing
and
we
the codes
needed
don't talk.
was that the two set of generators, which today she didn't mention, she mentioned it yesterday, that they be totally non-conjugate.
Yes.
No element of A will be
Right.
conjugate to no element of B. Now, that's a little bit delicate issue because basically in the examples that usually we construct Cayley graphs, we have an infinite group and we pick the generators there and we look at quotients. Now, in the infinite group, you can take many set of generators and you can easily make them not to be conjugate.
But in
It's possible.
in the quotients, they may become conjugate.
Right, and not only, there are actually, this subject was studied by people in a different connection. You know, you can take two matrices of, say, SL3Z, which are not conjugate, but they conjugate mod P for every P even.
But Alex, if out of the A times B pairs that may collapse, at most A plus B will collapse.
Yes.
Okay, so it's true.
So it's not really, it will not affect anything in the
You're
analysis.
probably right, but we have it because of, Avi, we have it, you know why? Because of you, because for conjecture.
Pay me later.
No, because you asked some question and then I developed some question and then I'm using the same trick.
So, but you didn't answer my question. What are G, A, and B?
So G is like PSL2 of some fields, and we have several versions that we take some generators of them. You know, in this LVS paper of the Ramanujan complexes, there are also construction in dimension in SL2, which give new Ramanujan graph that somehow we never paid attention to them because who cares? At that time, there were many Ramanujan graphs already, and some of them can help here. There is another argument one can take one of the version of Morgenstern that you take the fields to be in characteristic 2 specifically, and then you can do using them. So, I mean, I can talk about that, but it's basically, it's nothing really substantially new, but it's kind of using some of the old results, just making, okay, sorry, yeah, I have to say something. How we ensure that they are not conjugate? The method is very primitive. We take one set of generators.
Of order 3.
Well, you know, we think of them as of infinite groups, so they have a large curve, which means, in an explicit way, which means that from one point, for some prime and more, the order is more than 2, and we take set of generators, which all of them are of order 2.
Mhm.
And then they're not conjugate even downstairs.
Right, because
I
then
don't want the union to be an
That's a
expander,
two-point
just
way.
take one.
Should be a more clever.
If only the union needs to be an expander, then just take one set of generators, divide it into two, and you will have it for free, I think.
why? It could be that A times that for A1, this equals A2.
But it's only for one G, it's only for one G. Right? I mean, every pair that's conjugate would ruin one G, so there's a constant number of vertices in G that would be affected. It doesn't affect anything else.
Yeah, maybe it's not a problem at all. You're right.
It's not a real problem. I think that anything you do will work. I mean, like take one set of generators and split it to two if you don't care about the exact relation between, because lambda is so much smaller than D that it doesn't matter to change D into D over two. Or you can take one set and take products of elements of it. I don't think it's a problem.
Yeah, also you can probably indeed just like delete a constant number of vertices from your graph.
But anyway, it would be ugly. There is no reason not to have a clean, elegant, full construction that works. And that's what we saw.
Work on that in a previous paper that we can quote.
Okay, more questions.
Okay, all right.
So something, I mean, I'm missing something. So for these A's and B's, you know from all the results that you have the CA and CB and they have all the properties that you want. The property of CA tensor CB, it's automatically true. You have to prove it.
You have to prove it. You made a definition here, right?
Right. So you have to show
Oh,
that.
it's agreement testable if blah, 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 blah.
So you have to find the parameter that show that it's.
To find
Right,
the
but
code,
there's
you have
these
to find such code.
Papers from 15 years ago that already show that random LDPC codes have this problem.
Okay. So this is also something that.
Yeah, but this is unrelated to A and B.
Yeah, unrelated to, yeah, just to their size.
Just
I see.
So, if you want to be formal, you say random LDPCs for some n0, for every n above n0, a random LDPC with appropriate parameters will have all the three properties you need, the testability, the distance, and the rate. And then, okay, so you have this n0. Now you need to find the sets capital A and capital B of size at least n0, and their lambda needs to be smaller than the parameter of the k you had here. And then combine it all.
More questions? All right, thanks a lot.
Thank you.